Hello, and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Welcome in to all of our viewers from around the world. Please let us know where you are watching from. And also, welcome into listeners on the podcast version of SETI Live, available on most podcast platforms. All right, everyone, get ready to giggle and make bad jokes. Let's all get it out of our system. Uranus is back in the news. In 1986, Voyager 2 flew by the distant ice giant and made a strange discovery. The planet's magnetic field was weird. Not just weird, unlike every other planet in the solar system. And for nearly 40 years, scientists have tried to understand why. So, to solve the mystery, they went back into the data collected by Voyager 2 and found a cosmic coincidence. That cosmic coincidence, of all things, involved the solar wind. Again, make the jokes, have fun. Joining me today is Jamie Jasinski from NASA's JPL, who is the lead author on the paper discussing this research. So we're going to have a nice chat, have a good time, and thank you, Jamie, for being here today.
Thanks for having me on. I'm glad to be here.
So, Jamie, do you have any good Uranus jokes to tell, or are we just going to let the audience run with
I'll
that?
let other people make the jokes.
All right. All right. Sounds good. Sounds good. I mean, I'm already going to apologize for the title on this one because I just couldn't resist and I tried to have some restraint, and then my colleagues were all like, "No, you got to do it." So the title for this one is Uranus breaks solar wind. I'm sorry. I'm really, really, really sorry, everybody. But if it gets you here watching, all the better. All right, Jamie, tell us about the Voyager 2 results. What did Voyager 2 see that got everybody's attention?
Yeah, so in 1986, Voyager 2 flew past Uranus. The flyby lasted about 5 days. When we're looking at the magnetic field, it was around 5 days. Obviously, when you're taking pictures, then it was a bit shorter because you have to be closer to the planet. And during those 5 days, we made measurements of the local space environment. So that includes the magnetic fields of the planet and plasma. So plasma is a charged gas. So you take a regular gas and you heat it up and you essentially break up the atoms so that they're now charged particles, so a proton and an electron. And so this plasma, which is essentially is the most common form of matter throughout the solar system. It forms around 99% of all the matter in the universe, is what we measured during the flyby, as well as energetic particles. And so this 5 days essentially are the only measurements we've had of the magnetic field and the plasma. Uh, uh, you know, that's the only measurements we have at all, the 5 day flyby. So all our understanding is from those 5 days. And we saw some very strange stuff. So Uranus, I don't know if everyone's familiar with Uranus. Uranus, unlike other planets, it's rolling on its side, so it's tilted very much 90 degrees off, and it's essentially the pole is pointing towards the sun during the summer. And whereas other planets orbit around the sun and they're spinning, this Uranus rolls. So that's already very strange. And then the magnetic field is offset by another 60 degrees. So if you're rotating this planet, the magnetic field is constantly essentially doing a big swirling motion and changing shape every half day. And so this is also one of the big results from that flyby. Now, the two other sort of strange observations, so those are sort of parameters that are very unlikely to change.
Mhm.
Uranus will always be on its side in the near future, and the magnetic field will be offset as well. But two other things that sort of perplexed us for the last 40 years is the fact that when we flew through that magnetic bubble that we call the magnetosphere, we didn't observe any plasma, very low densities, such low densities that we've called it a vacuum magnetosphere for the last 40 years. And this is unexpected because although generally when we talk about space, everyone says space is a vacuum, this isn't so because we have that plasma, and we didn't really observe anything. And then the other big mystery was that we observed very intense radiation belts. So radiation belts are this very narrow band of very energetic particles, so energetic particle radiation, that's very close to the planet. And Jupiter has the most intense radiation belts, and Uranus was a close second. And a mystery of that, of what, of the mystery of surrounding the radiation belts is due to the fact that where are these particles coming from? So if we have these energetic particles in the radiation belts, but we have a vacuum magnetosphere, how are we essentially creating these radiation belts? So usually in magnetospheres, the plasma in the magnetosphere feeds those radiation belts. And if you have no plasma in the magnetosphere, then how are you generating these intense radiation belts? And then also we observed plasma waves in the magnetosphere, which remove the radiation belts. So how does radiation belt exist when it doesn't have a source and also has very efficient loss mechanisms? So that was a big mystery for lots of years. So that was a lot of info in just a quick summary of Voyager 2 during the flyby.
So I'll sum it up here. So we have 5 days worth of data from this Voyager flyby that reveals that Uranus is missing certain aspects of the magnetosphere that we would expect to find based on observations of basically every other planet in our solar system. And for 40 years, everybody sort of sat around going, well, Uranus is just weird. I mean, it's on its side, it's rolling around. So, you know, there could be any number of reasons why this is strange. What motivated you and your team to dig back into this Voyager 2 data? Because that is really truly all we have here, to sort of find out what really was the case. Because you actually have a logical solution for this that is not just, well, Uranus is weird. So what motivated your team to delve back into this?
I guess I never really truly believed that the results were representative necessarily of what's happening all the time. So I've previously worked on missions that orbit a planet for many years. So I've worked on Cassini, which orbited Saturn for 14 years, and Messenger, which orbited Mercury for 4 years. And so you get a lot of observations of the magnetosphere and the plasma dynamics. And over the course of those very long missions, you see a lot of variation and a lot of change. And I just thought, what if we just, if something was just happening at that time to have caused it to be like that? So a great example of this is from Mercury. So 4 years worth of messenger data at Mercury. Mercury being the closest planet to the sun, messenger did around 4,000 orbits over the course of 4 Earth years. And for 4 of those orbits, we observed the whole entire magnetic field essentially disappear because plasma from the sun smashed into it, coronal mass ejection. So this is an ejection from the sun, hit Mercury and essentially tore up the whole magnetic field. And during these full flybys, we essentially didn't measure the magnetic field of Mercury. And so if you had made a flyby just during that time and then didn't really look at what's going on, you would think, well, Mercury just doesn't have a magnetic field and maybe it's just like this all the time. So I wanted to understand the solar wind and what was happening outside of Uranus to maybe have caused this or had an impact on the possible results that Voyager 2 took at the time.
I'm going to talk to you some more about the results. I'm just going to welcome in people where they're watching from. So far, we have, let's see, Bolivia, the UK, Arizona, and I also know that's my friend in Georgia. So here in Silicon Valley, welcome in. Sweden, Brazil, and Florida. So Miami Beach. Ooh, that sounds kind of lovely. It's been rainy and cold here, so I'm with you on that. And I'm not a big Florida fan. I've lived there, but that sounds nice. Okay, so Jamie, tell us what the results were that you found. So explain for us why Uranus had this weird magnetosphere going for it.
Yeah, so We looked at the data from the solar wind. So the solar wind is the plasma, that charged gas that's constantly flowing out from the sun, and it's flowing outwards past all the planets throughout the solar system. So as it travels outwards, it's essentially hits the magnetic field of a planet and then is forced to essentially flow around it because it can't penetrate the magnetic field.
Right.
And this plasma, Voyager 2 was measuring throughout its voyage throughout the solar system. So in the days, weeks, and months and years before it arrived at Uranus, it was constantly measuring the solar wind. So you have a constant understanding of what's happening of the plasma conditions that are coming from the sun. And as the solar wind hits a planetary magnetic field, it exerts a pressure onto the magnetic field. So it essentially can push down on it. So if the density increases or the pressure of the solar wind increases, you essentially push on the magnetic field until the pressure of the magnetic field essentially pushes back and it's back into balance. So the size of the magnetic field or the magnetosphere is constantly changing because it's a fluid, constantly varying state because nothing's ever steady. So looking back over the solar wind data, you can see what's happening. And we saw that in the days just before Voyager 2 got there, that solar wind dynamic pressure went up, and it went up a lot. So if we had arrived a week earlier, the dynamic pressure would have been 25 times less, and that's a significant increase over the course of a few days.
Yeah,
And
that's a huge change.
yeah,
That's a lot.
it's not a small change. It's very significant and very and has important consequences. So taking that solar wind data, you can essentially calculate the size of the magnetosphere. You take the crossing that we actually observed. So when Voyager 2 passed from the solar wind into the magnetosphere, you can use that to fit a very simple pressure balance equation. And from there, you can essentially estimate the size of the magnetosphere that it was for that week before, and then slowly watch it shrink as you're getting closer to Uranus. So the simple calculations that we can make, we can estimate essentially that the magnetosphere was about 5 times bigger a week earlier in volume. So we shrunk it to about 20% of its size in the course of a week before Voyager 2 got there.
Wow.
And so you're essentially taking this big system and you're shrinking it, and that type of squashing can drive a lot of dynamics in the system and can affect all of the magnetospheric measurements we made at the time, including pushing out all the plasma out of the system. So generating that vacuum magnetosphere. So you're essentially increasing your loss from the magnetosphere by driving all this plasma out. And also, whilst you're driving that, you're essentially pushing that plasma into the radiation belts, which then can be energized and form the very intense radiation belts we observed. So you can answer the vacuum magnetosphere, and you can also answer the intense electron radiation belts as well.
So you essentially got two birds with one stone in this reevaluation.
Yes. Because it's all a dynamic system and it's all very coupled. The whole system with the moons and the rings is coupled through the magnetic field, and they're all joined because they're tied essentially through the magnetic field. So there are a lot of things that can be explained with that due to the squashing of the magnetic field, including some of the strange observations we had from the moons. So one of the sort of side mysteries of the vacuum magnetosphere was the fact that we observed no heavy ions. So ions are just, if it's hydrogen, it's just a proton and an electron. So the proton is the ion, but you can form other ions. So if you have water, you can create water group ions. So at Saturn, we have the moon Enceladus, and Enceladus is constantly releasing water. And that water gets ionized, and then we observe it in the magnetosphere of Saturn. So you don't have to be near the moon to measure that water. because it's trapped in the magnetic field. So you can be far away from the moon and still measure the water from Enceladus in the magnetosphere. So a big question at Uranus was, why didn't we observe any heavy ions? Because we have 5 icy moons at Uranus, and you would expect some kind of water contribution, heavy ions that we would measure with Voyager 2, and we didn't. And then the other interesting part was that we didn't observe any alpha particles. So this is helium, and helium comes from the solar wind. And I thought that that was particularly interesting because you would expect some helium to be sort of trickling into the system. But if you're not observing any of it, it can only really be explained by the fact that you've just pushed all that plasma out. So that was a quite an interesting discovery that Voyager 2 made, and that's also explained by the fact that you can squash this mechanism. And it's also not just water. So we have an icy moon at Saturn called Rhea, and it has a CO2 atmosphere, and you measure those CO2 ions in the plasma at Saturn as well. So we just didn't observe any heavy ions other than protons at Uranus.
So you have a graphic, and I want to make sure that we get to this because this is a really clarifying graphic. So oh, sorry. What Hasmin and I are fighting over controls. So what does this graphic show us?
This graphic was made by a great JPL graphic artist called Lisa to try and explain what's happening during the Voyager 2 flyby and just before. So the graphic on the left shows you the sort of picture of the week before. We have the sun in the far distance. Obviously, in this particular schematic, it's shown a bit bigger just for illustrative.
Not to scale, everyone. Not to scale.
Yeah. And you have the blue sort of curve shows you the extent of the magnetic field of Uranus, and it's labeled as a big magnetic bubble. So this would be your magnetosphere. So we would say it's a big magnetosphere. And then inside you have the sort of purpley shading is supposed to represent the sort of a dense plasma from the moons, from the planet itself, and possibly the rings are sort of trapped in the magnetic system. And then you have weak radiation belts there listed as well. And then on the right, it sort of shows you the arrival of this dense plasma from the sun. So they're called co-rotating interaction regions. So they're connected to the sun and they're rotating outwards, and essentially they rotate every 28 days. And this was the most intense co-rotating interaction region of a whole 9-month period at Uranus. So this was the biggest at the time. So this sort of this sort of region can swing past Uranus many times, but it will vary. And this was the most intense in that time frame. And you can see it sort of hitting the magnetic bubble. And now it says small magnetic bubble. So you've shrunk that magnetosphere. And now the plasma has left, and you have these intense radiation belts. So this sort of gives you a schematic that illustrates of what was happening before and during the Voyager 2 flyby from a sort of plasma and magnetospheric perspective.
That is really interesting, and I shout out for this graphic because it really kind of clarified things for me. So basically, this plasma, essentially the solar wind, full of all of this very dense plasma, comes in and kind of strips the magnetic bubble down. Is that how this works?
Rather than stripping, it's more pushing.
Pushing, okay.
So there is another process which happens at these magnetospheres where you're essentially joining the magnetic field of the solar wind to the magnetosphere, and therefore you can sort of strip the day side, but that's not really what's going on in this particular picture. That's what, when I was giving you the Mercury case, that's what happened to strip the magnetic field,
right,
when we observed it with Messenger. So that is technically does happen, but not in this particular picture.
Not in this.
It's more of a sort of a pushing, sort of squashing scenario.
So it's coming in and it's just sort of like so dense that it's shoving this sort of downward. Okay.
Yeah, pushing it down. It's like if you have in your garden a hose with water and there's a trickle, and then you really turn it up, and you blast it at your grass or your plants, and the plants then get flattened. It's that sort of difference. It's sort of the pressure of the water essentially increases on the flowing of the in your garden, and so this you can kind of imagine it in that way.
Okay, so it's more of sort of like a direct pressure rather than sort of a skimming, right?
Yeah.
Okay.
Yeah.
So I'm going to welcome in. I think there was a couple more. I think we have Alabama, and then there were a couple more people that said hello but did not give locations. Let us know where you're watching from. I like to know these things. So if you have questions for Jamie, please put those in the comments, and we will do our best to get to them. Jamie, what is sort of next on this research? Is this you've answered the question and you're done, or is there more to come here?
No, I think so. This provides, I think, up until now, the most reasonable, simple explanation. But we know so little, and Uranus generally is so strange because of that tilt of the planet and the tilt of the magnetic field, which is totally different to every planet we've studied. That a lot of we don't know a lot of the sort of dynamics that will happen at a planet that has that sort of configuration. We base a lot of this physics on well-studied planets like Jupiter and Saturn and Earth, because we've studied those magnetospheres very significantly with a lot of different spacecraft.
Mm-hmm.
But the next thing really to do is to go back to Uranus. So 2 years ago, there was the National Academy of Sciences, a report that essentially they do a report every 10 years that provides priorities towards NASA, and they suggested that the biggest unanswered sort of question in Uranus currently in the solar system is Uranus, and that we should do a mission back to Uranus. So this would include most likely an orbiter and possibly a probe. The draft concept mission was called Uranus Orbiter and Probe, so it's called UOP. It's still sort of a concept at the moment. Hopefully, at some point in the future, this will come to fruition, and we'll hopefully launch a mission like that and go back to Uranus in the coming decades. That will take a long time frame, obviously, because building these missions take a while. Generally, for a large mission like this, the usual ballpark is around 10 years to build such a large mission. Mm-hmm. And then Uranus is so far away, it will take us over 10 years. So between 10 and 15 years is generally what the type of orbital trajectories we're talking about to get in that sort of time. You get there in that sort of time frame with the kind of spacecraft that we usually build to get to these missions, to get to these planets in the outer solar system. And then you would orbit the planet and take measurements of the magnetic field over a couple or a number of years, and therefore study it in much more detail. And obviously, this wouldn't just be a magnetospheric mission. There would be a lot of studies about the moons and the planet and the rings. A key result of this paper is to study subsurface moons, subsurface liquid water oceans at these moons. So I mentioned
that was going to be my next question: is what does all of this mean? So of course, we're here at SETI, and that's search for extraterrestrial intelligence, but we all pretty much presume at this point that the first life we find will be more on the microbiotic side of things, and one of those places that we're always looking, that we're trying to look are these icy moons with subsurface oceans. So what does this magnetic field result give us hope for at Uranus? How does that help the moons?
So there are 5 major uranium moons, and the outer 2 are considered the most likely have a subsurface liquid water ocean. So Europa is a moon of Jupiter, and NASA's JPL has just launched a mission to Europa called Europa Clipper to study that subsurface liquid water ocean, which has more water under its surface than all the oceans on Earth combined. And the way you do that is by measuring the magnetic field of the ocean itself. So Uranus has a big magnetic field that the moon sits in, and this is constantly changing. And because there's a changing magnetic field, you can drive currents in the subsurface ocean, and those currents then generate their own magnetic field. And as you fly past the moon, you can measure that change in the magnetic field, and that change will directly correspond to the size, depth, and salinity of the ocean. Before this most recent results, Titania and Oberon, the two outermost moons, are on the edge of sort of the Uranus system, and that Oberon was sort of sitting in the solar wind, and Titania was sort of skirting the boundary of the magnetosphere. So we were thinking that to really study this signal, the magnetic signal, will be quite tricky because Oberon's no longer sitting in the magnetosphere, so you're losing that change in magnetic field that Uranus provides to drive that repeatable, predictable signal. And so you wouldn't be able to really do accurate, reliable magnetic induction studies without very specific trajectory requirements. But now, because we know that the magnetosphere was very small during that time of the Voyager 2 mission, and generally it's a lot bigger, we've come up with averages and distributions now to sort of calculate and quantify the size of the magnetosphere. There's a very low chance that Titania it's around 3%, and Oberon it's around 12%, that they orbit outside the magnetosphere. So they're very likely to be sitting in the magnetosphere for most of the time, and that we will be able to actually try and study whether there is a subsurface ocean.
That's exciting. Orbiters for every planet, please. I'm gonna welcome in some last people, and then I do have a couple audience questions to ask. Let's see. We have another person from Georgia, Romania, Oregon, and Austria. So welcome in, welcome in. All right, Jamie, the first question I want to ask, it looks like someone is looking for some clarification here. The weak radiation belts are turning intense simply because of this compression by the solar wind. Is that the mechanic that's working?
Yeah, so at Saturn, we know that when we have observed these co-rotating interaction regions which compress Saturn's magnetosphere, you can actually see enhancements in the radiation belts of Saturn that can last a number of days. And also at Earth, we have seen cases where you see an increase in the fluxes of energetic particles in the radiation belts. And that population that essentially feeds the radiation belts at Earth increases when you have these co-rotating interaction regions arrive at Earth. So at both of these planets, we've seen this effect. So yeah.
Okay. And then you may not have the answer to this question. I'm not sure even I have the answer to this question, but I'm gonna throw this one up here anyway. Martin is asking, does Uranus's color, as it's been analyzed, turn out to be more blue than green? And why was it sort of changed from that?
Yeah, I'm not the best person to ask about the color of Uranus. I thought it was the fact that the result was that Neptune is less dark blue than we thought, and actually Neptune's closer to the color of Uranus than we previously thought.
I think actually you're correct now that I'm trying to remember, because this kind of came about either earlier this year or late last year, where they reanalyzed the processing that they had done on the filters, and decided that the original processing had made it a little bit too blue, and that they really were closer in color to each other because their composition is fairly similar.
Yeah, so yeah, it's just an instrument analysis effect, I guess, as you described. So that's down to human error, I guess.
All right, and last question, because I do feel like this is definitely how we wanted to kind of cap this show off. But How badly do you want a Uranus orbiter?
Yeah, it would be extremely exciting. This is something that we've been thinking about. Well, I've been thinking about since the start of my PhD over a decade ago now. My PhD supervisor was leading the charge in Europe for a Uranus orbiter, which wasn't selected. And so it's sort of been a big dream of many magnetospheric scientists to have a mission go back to Uranus. So yeah, we would all be very excited if when and if it happens.
I am right there with you. More orbiters, please. I'd like one at Neptune as well. I'm gonna hold out as well. So Jamie, what is directly next for you? You're at AGU right now. But
Mm.
what are you currently working on? What's next? What can we expect from you personally?
Uh, More Uranus data analysis and Neptune data analysis. And also, I've been working on some Mercury science as well, because I still work on Mercury. So, one of the topics I've been working on is understanding the sodium exosphere. So, Mercury has this
Hmm.
layer of sodium. It's not an atmosphere, it's an exosphere, and how that is produced, because we think it's a direct relation, or we think it might be, of plasma from the solar wind essentially hitting the surface and then releasing it. But then there's also other effects. So that's one of the possible mechanisms. It's mostly just photons from the sun hitting the surface and releasing it. But from the plasma side, we've been looking at the times when we observe plasma entering into the magnetosphere. So yeah, Mercury science and Uranus and Neptune.
Well, the next time that you have another paper out, you please let us know. Would love to have you back. This has been fantastic, and I'm really excited and hopeful that we will get that Uranus orbiter, hopefully within our lifetimes. That would be nice, NASA, please. Pretty please, NASA. So Jamie, thank you for joining me today. Thank you everybody for watching. We really appreciate all of your support and of course, all of the science. We are the SETI Institute, a 501c3 nonprofit in Mountain View, California. And shows like this, all of our outreach are driven by your donations. So your bits, your super chats, your subscriptions on Twitch, all of these things are what keep us running this program. So thank you so much for watching and thank you for being here. Please make sure that you like, subscribe, comment, share all of the various video things that we beg you for. And we will see you next week on Study Live when I will have Rebecca Charbonneau here to talk about her new book, Mixed Signals, which looks at alien communications during the Cold War, the Soviet era. So we're going to talk about all of that next week. So stay tuned for that. And Jamie, thank you again for being here. Thank you, everybody, for watching. Have a wonderful rest of the week, everyone.
Thank you.